We can't see exactly what severe hazards a storm is producing from satellite imagery like we can on radar. But severe storms do tend to display some certain features and signatures, and that can help you out in the field when you're trying to determine which storm to target or see which storm is most intense. Let's say you're out on a storm chase in western Oklahoma, you're sitting and waiting, and then multiple storms begin to fire in your target. Your job is to figure out which of these storms is going to be most intense and which of these storms you want to target. And as you can see, there are multiple storms firing in our target area, but there's really not a ton of difference among them just looking at radar. You see the storm here north of I-40, the one just south of I-40, and then the southernmost one down there. Really not a ton of difference between these storms just looking at the radar. That's where infrared satellite comes in. Infrared satellite measures brightness temperature, essentially an estimate of the temperatures of the tops of the clouds. Taller, more robust, more intense storms tend to have colder cloud tops, those oranges, reds, and even blacks you see on infrared satellite imagery. So in these situations in which you have multiple storms to choose from, infrared satellite is a great tool to use to identify which storm is perhaps your target storm, which storm is most intense. And you can do that by comparing the cloud top temperatures of each storm. You're looking for the most persistent, coldest cloud tops. So in our western Oklahoma example here, you see all of our storms lined up in western Oklahoma. All of them are displaying fairly cold cloud tops, but watch that southernmost storm here. It seems to display the coldest cloud tops for the most extended period of time, even showing some of those black colors indicating very cold cloud tops, while the cloud tops of the other storms seem to be warming a little bit, indicating weakening. So this would give you a clue that that southernmost storm would be the one you'd want to target. It seems to be the most persistently robust storm of the bunch and would have the highest chance of producing severe weather. Now, it's fairly common to see fluctuations in which storm has the coldest cloud tops. As you see here, all the storms have some sort of cold cloud tops. They kind of trade off for a little bit. Initially, this northernmost storm seems to have the coldest cloud tops. Then it transfers to one of the middle storms there. But that southernmost storm has the most persistent, coldest cloud tops, those very cold cloud tops, which are the coldest that we've seen of any of the storms, getting into those black colors. And it's had that for the longest amount of time. So that storm is the most persistently robust, and that would be a sign that you might want to target that particular storm. Now, speaking of this small spot of very cold cloud top temperatures within the anvil, that is indicative of a feature called an overshooting top. And if you've ever seen a thunderstorm from a distance before, you've probably seen an overshooting top. Thunderstorm updrafts are quite intense. The flow within them can be traveling at 100 miles per hour or more in some of the strongest storms. But when the updraft hits a layer of the atmosphere called the tropopause, it flattens out. That's what gives the cumulonimbus clouds their anvil-type shape. What happens is the updraft goes up and up and up until it hits the tropopause, above which is the stratosphere. In the stratosphere, temperature tends to increase with height, which is unfavorable for convection. So the updraft goes up, hits that tropopause, which is the interface between the troposphere, where most of our weather happens, and the stratosphere. It hits that tropopause and flattens out because it just can't go up anymore as the temperature of the environment starts to increase with height. But the updraft is moving so rapidly in some of the strongest storms that its momentum carries it up into the stratosphere just a little bit, and you get a little bit of a dome-shaped bubble on top of the anvil, which denotes the portion of the updraft going into the stratosphere. That is your overshooting top. So an overshooting top is usually a sign that a storm is quite intense. Overshooting tops, as we mentioned, show up well in infrared satellite imagery as these kind of dots of extremely cold cloud top temperatures within the anvil, but they also show up well in visible satellite imagery as these kind of bubbly areas that seem to be rising above the rest of the anvil. This will also be co-located with the signature in infrared imagery. This is a pretty textbook example of an overshooting top, particularly with the southern storm. The very bubbly area right there, rising above the rest of the anvil, is your overshooting top, which is co-located with that darker area in infrared satellite imagery.
The Chaser Academy is the best deal in storm chasing, and it costs less than a combo meal at McDonald's. Unlock instant access to exclusive storm chasing presentations, participate in live group coaching sessions, and get answers to all of your questions in the unlimited Q&A chat. Whether you're a beginner, a veteran, or somewhere in between, our expert coaches will help you take your storm chasing experience to the next level. Click the join button below this video or on our profile page and enroll in the Chaser Academy right now.
Another signature you might see in infrared satellite imagery that indicates an intense storm is the enhanced V signature. The enhanced V is the satellite equivalent of the V-notch radar signature that we talked about in the Radar Foundations module here in the Chaser Academy. The enhanced V is a V-shaped band of colder cloud top temperatures that surround the overshooting top. So here is your overshooting top right there. And then you have this V-shaped or boomerang-shaped band of colder cloud top temperatures surrounding that overshooting top. The reason an enhanced V signature forms is because the updraft acts as a barrier to flow. Just like, say, a mountain acts as a barrier to flow, so does a strong updraft. So say, for example, we're looking straight down at a thunderstorm updraft. Air can't go through the updraft, so what happens is it gets diverted around the updraft, and that's how you get that enhanced V signature, that V-shaped band of colder cloud tops around the overshooting top. Again, an enhanced V signature is a good sign that your storm is quite intense. In fact, it has been shown to be an excellent precursor to the onset of severe hazards within storms, generally with a median lead time of about 30 minutes, meaning that the development of the enhanced V usually precedes the first severe weather hazards occurring within a storm by about 30 minutes or so. This is a textbook example, very clear example of an enhanced V signature. Again, here is your overshooting top, and here is that band, boomerang-shaped band of colder cloud top temperatures surrounding the overshooting top. And here are a couple more examples. There is your overshooting top right here, band of colder cloud tops surrounding that overshooting top. And a slightly more subtle example, this storm in the upper right-hand corner of the image. Notice your area of coldest cloud top temperatures there, and this band of orange colors surrounding that in that V-shaped manner. That is your enhanced V. Now, not all severe storms produce enhanced V signatures, but a good percentage of them do, and you can be sure that if you see an enhanced V signature on infrared satellite imagery, that storm is quite intense and could very well be producing or produce severe weather in short order. Another signature that's related to the overshooting top is the Above-Anvil cirrus plume. These are areas of cirrus clouds that exist several kilometers above the anvil of a thunderstorm that are caused by gravity waves as the updraft or overshooting top penetrates into the stratosphere. I always use the analogy with gravity waves of throwing a rock into a calm pond. As the rock enters the pond, it's going to make ripples that move outward from where the rock went in. Same thing with gravity waves, and in this case, it is when the updraft or overshooting top penetrates into the stable layer of the stratosphere. As it does that, that energy is kind of dispersed outward, and you get gravity waves. And this sometimes allows a plume of cirrus clouds to form, and that is the Above-Anvil cirrus plume. And in this image here, which is taken from Bedka et al. 2018, the white dashed lines indicate examples of Above-Anvil cirrus plumes, with visible imagery on the left and infrared imagery on the right. Above-Anvil cirrus plumes can be pretty difficult to identify on satellite imagery. They're easier to see in visible satellite imagery. Notice on the left here in the dashed white outlines the kind of wispy band of clouds that's emanating and flowing downstream from the overshooting top. That is your Above-Anvil cirrus plume. Same thing down here with this southern storm. You have your overshooting top here, and then the wispy area of clouds within the white dashed outline. That is your Above-Anvil cirrus plume. They can also be seen in infrared satellite imagery, but there's not really a standard signature that you'll see in infrared imagery when an Above-Anvil cirrus plume exists. Oftentimes, they'll be demarcated by an area of warmer cloud top temperatures downstream from the overshooting top, and oftentimes they'll be embedded within the enhanced V signature, as you see here with the southernmost storm. But as you notice with the northern storm, there really isn't a significant area of warmer cloud top temperatures within the area of the above-anvil cirrus plume. So infrared imagery can be a little bit wishy-washy as far as showing a signal of an above-anvil cirrus plume, but most often you're going to be seeing them in visible satellite imagery as you see on the left. Here are a couple of examples of above-anvil cirrus plumes on visible satellite imagery. This first one is actually from the infamous Gerald, Texas F5 on May 27, 1997. The supercell that spawned the Gerald tornado is the southernmost storm, so keep your eye focused on that storm. You can clearly see the overshooting top in the anvil there. As we go forward with this loop, you can see a very defined plume of wispier clouds emanating downstream from the overshooting top. That little bit of wispiness there downstream from the overshooting top, that is your above-anvil cirrus plume. Here is another example. Keep your eye on the southernmost storm here as well. There is your overshooting top. So look just to the east of there as I play the loop here. You'll see a well-defined area of those wispier cirrus clouds that flow downstream from the overshooting top. You can really see it in this image here, that wispy plume right in there. That is your above-anvil cirrus plume. This example is pretty well defined. Again, they're not always going to be this well defined, but these two examples were pretty textbook examples of above-anvil cirrus plumes. Like overshooting tops and enhanced V signatures, above-anvil cirrus plumes indicate that a storm is very robust. In fact, above-anvil cirrus plumes tend to only exist in the most robust storms with the highest and coldest of cloud tops, and oftentimes supercells will display above-anvil cirrus plumes. And similar to the enhanced V signature, the lead time between the first signs of development of the above-anvil cirrus plume and the onset of severe weather hazards from a given storm tends to be over 30 minutes on average, so it's an excellent precursor to the onset of severe weather. And finally, sometimes you may see bands of cumulus clouds flowing into a thunderstorm on visible satellite imagery. This is a sign that the storm has healthy, warm, moist inflow. Taking a look at this example here, focus your eyes on this southern storm here, and on its southwest flank you can see a band of cumulus leading into the storm. And as it matures and becomes a little bit more intense, you can see all these bands of cumulus flowing into the storm on its southwestern flank. All of these clouds are flowing into the storm, denoting that the storm is experiencing healthy, warm, moist inflow. These bands can include the flanking line of a storm. The flanking line is a series of updrafts that feed into the main updraft of a supercell. If you've ever chased a supercell, you've probably seen a flanking line, and it looks something like this from the ground. That series of cumulus clouds that feed into the updraft base, the main updraft base of a supercell. And these can also involve just inflow feeder bands that flow into the supercell. In any case, these all promote supercell longevity. These are persistent sources of energy and really fuel that feed into the supercell. In terms of a flanking line, if for some reason the main updraft starts to dissipate a little bit, the next updraft in the flanking line can then take over and become the new dominant updraft. So anytime you see a look like this on satellite, that is indicative of a very intense supercell with healthy, warm, moist inflow. And this supercell, in this example, did go on to produce all severe hazards, including a few tornadoes.
Remember to check out those links in the description below, and then watch another video.